Okay, good evening, everyone. We are joined today by Vadim Pasko, the creator of SplineCloud, and this meeting is in collaboration with an aerospace faculty of the Kyiv Aviation Institute, where Vadim is also a PhD student. Vadim is Ukrainian engineer, and he saw the need for better knowledge sharing in engineering and science. And SplineCloud is his solution. He is in a platform to exchange data and results from the numerical experiments. The main idea to help engineers avoid repeating work, and also it helps to collaborate more efficiently. So with an SplineCloud, we can, let's say, boost innovation and make faster progress in engineering and science. So Vadim, you're welcome.
Svetoslav, thanks for introduction. Everyone, thank you for joining this webinar. Today will guide you through this topic of reusing the results of numerical experiments in design automation process. So basically, you can apply this to any design automation of any vehicle in mechanical engineering, but I want to particularly focus on unmanned aerial vehicle design, because this is probably something that is more resonating to you, the audience, and probably you are involved in this research. And since we're here with collaboration with Kyiv Aviation Institute, this topic should be interesting for most of us. And why I choose this topic? Nowadays we have lots of tools for conducting numerical experiments, but there are not much attention driven to how can we efficiently conduct these experiments and how we can reuse these results to better understand our designs, how to faster make decisions, and eventually how to automate design. And this is something that I want to share with you today. So I will quickly guide you through the agenda first. So first I will introduce myself, then I will cover basic topic of design phases in mechanical engineering, then I want to emphasize on the role of mathematical model as a core concept of mechanical engineering. And I want to focus more on the processes of knowledge formalization and reuse in the process of mathematical modeling. I will talk about reusable data and its role in design automation. And I will introduce you to SplineCloud, which is the platform for sharing and managing knowledge in engineering. And after that, I will switch to a use case. So I will explain how with all these concepts and tools, we can achieve efficient design automation. And I will speak about open source tools. So get ready for some new insights. Probably not, some tools will be new for you. Okay, so let me first speak a little bit about myself so you have a better understanding who I am and why I'm talking about this today. My name is Vadim. I have experience in aerospace engineer. I was working in the state design office Yuzhne for 10 years. This is the largest space company in Ukraine. And I was working always on conceptual design phases. So I was involved in numerous projects, starting from unmanned aerial vehicles to aircraft, space launch system, to lunar landers. I was also involved in exotic topic like space elevator and many more. So basically my career was always related to conceptual design. It's when you turn an idea into some prototype, into some digital prototype. And from my experience, this problem is really not trivial to tackle, because there is no standard ways to conceptualize your ideas. So there is always a high weight of creativity here. At the same time, there are some patterns that while used efficiently, can simplify this process. And this is what I will talk about today. So let's focus first on the very global aspect of things, is design phases in engineering. So especially when we talk about conceptual design, because there are later phases of design for manufacturing, product lifecycle management, and other things that we will not cover today. We are focusing more on the conceptual design. It's when we turn an idea into digital prototype. And efficient delivery of idea and understanding what are design parameters of our vehicle can be done only through mathematical modeling process. So if you are familiar with this, you would agree with me. If not, probably we can debate on that. But basically, the thing is that when you have an idea, you have to go through this formalization process, when you formalize the idea into some simplified mathematical model. And this model should be designed in a way that it should answer main design questions, and solve for the main design parameters that will eventually help you to optimize design and come out with a final prototype with all details defined. And with this process, mathematical model plays a crucial role in the whole engineering process, because if we make mistake on this stage, then fixing things on later stage will cost huge money, and it will turn back all the processes. So it is very important that we focus on mathematical modeling process and make correct mathematical models that answer main design questions. So what is mathematical modeling engineering essentially? So you may think of mathematical model as a set of equations on paper, but we live in the digitized world, and usually now we think of mathematical model more as a computer code, actually. Either we use Python, MATLAB, other languages. When we draft a model of something, our equations eventually end up in code. So, and this code essentially is based on existing knowledge. So we incorporate knowledge from different domains into our mathematical model, especially if we talk about some complex vehicles like aircraft, like humanitarian vehicles, maybe like this lunar rover that is on the picture here. So we incorporate knowledge, existing knowledge from different domains, and we incorporate best practices, our experience, data on material specifications, some experimental data. All this we collect to derive mathematical model. And during this process, we usually face the need to discover new knowledge, which in engineering always happens through experiments, through either numerical experiments or physical experiments. There is also a share of some statistical data that we can incorporate in our mathematical models, but I will not focus on that today. So the idea is that when we don't know how some part or some system behaves, we go and decide to conduct either physical or numerical experiment. And this new knowledge also have to be incorporated in our mathematical model to amplify this and add it with required data. And this mathematical model, once we have defined it, we can use it for design optimization process. But in engineering, it happens so that knowledge comes from various sources and in various forms. And you can really get frustrated by how to convert all this knowledge into mathematical models. And engineering software that currently we have complicates this process because of the proprietary data formats, because of the closed corporate ecosystems. And we can say now that on the contrary to other domains, engineering knowledge lacks accessibility and it has weak reusability. But to understand this, how we can, what is reusability, right? We should understand the process of how we can transform knowledge into mathematical model. And this happens through so-called knowledge reuse process. So, I'm sorry. So there are two general types of knowledge. It's either explicit knowledge or tacit knowledge. It's knowledge in engineering. So explicit knowledge is simple. It's either laws of physics or design manuals, some engineering standards, something that has a written form, something that has already been covered in some documents. While tacit knowledge is something that wasn't really covered. It's based on our observations, our experience, some best practices in engineering, perhaps. But in order for us to make a mathematical model, we need to convert all these types of knowledge into reusable formats. And these reusable formats have clearly defined properties. There are only three possible forms of this knowledge. It's either data, functions, or algorithms. You may think of functions as being part of algorithms, but I explicitly excluded these because functions can be inherent to data. So we can find out relations in data and convert it into functions. So in this way, functions something that is stand out from data and algorithms in my perspective. And efficient reuse of data, functions, and algorithms is in code. It depends on the level of reusability, both for data, functions, and algorithms. So for algorithms, there is general patterns, programming patterns, how to make reusable code. For data, it's I will talk a little bit later about this. And for functions, there is also some general recommendations, what functions can be considered reusable. And by reusable, we mean mathematical model. So it also depends on our software that we use for mathematical modeling, our expertise in programming, and maybe some side services that can help us, and so on. But first, let's take a look at the formalization process and knowledge formalization. So in engineering, there are generally two types of sources of knowledge. It's either experimental data, simulation results, specifications of some properties and materials, and these things we can convert into data sets and functions. So with this process, we extract data and formalize it, attach metadata description to that, and usually happens so that this data say something about the relations, how one parameter relates to another parameter. And the ideal case is when we extract not only data sets, but also functions between parameters, because they are more reusable in our mathematical models. On the other hand, the knowledge that represents design methodologies, some best practices, and advices on what materials to use in which cases, this can be converted into algorithms. So we can define algorithms based on these practices, how we can approach design. And with the new tools like ChatGPT and other AI tools, we can be more efficient in this process. I personally used ChatGPT to develop mathematical models, especially when I was new to some problem. I asked it to extract some domain knowledge and create mathematical model for me in the set of equations. And then I asked it to create Python code for that. And I was amazed how fast it converged to the things that I then later discovered in handbooks. So I welcome you to explore this possibility, but I'm sure you're already familiar with that approach. And when we talk about algorithms, they usually can be based on data sets and functions. And currently there is a trend in developing new AI for engineering, new AI tools for engineering that are based on the approach of training AI agents, AI models on the tons of simulation data. So you may have seen such projects. I have seen such on LinkedIn. And there is one concern about this approach is the abundance of data and the state of data. And this is why reusability of data is so important here. So we not only can facilitate ourselves, but also facilitate AI agents to be more efficient when we have reusable data. But what is reusable data? So generally, when we speak about reusability, we also mean other things. We mean findability, accessibility, and interoperability. The thing is that there is a term fair, which means all these things, but the last word in this term, reusability, is something special because findable, accessible is well defined, so you can apply it for many different domains of knowledge, so you can apply it for different data. Interoperable is, well, it depends on what is data itself, but at least we can say about some basic formats, data formats that we can consider interoperable. But reusable is something that really specific to domain of knowledge. And by reusable in mathematical modeling process, which we are really focused on today, we should say that reusable data is something that is explainable, well documented, clean, and we can trace the ownership and history, version history probably. And most importantly, it is automation ready, meaning that this data should be placed on some resource that allows us for building automatic pipelines to write code to retrieve this data efficiently, to retrieve clean data. And to understand what, on the contrary, we can say what is non-reusable data. We can think of the data on hard drives, which are not accessible, meaning they are really hard to reuse. We can think of corporate databases with limited access. We can think of proprietary formats, maybe even binary formats that we don't know how to open and how to integrate with some services and so on. We can also think of Excel files with multiple tables on one sheet without proper description. You will waste tons of time understanding what happens on those Excel files. Probably you already done such tables. I have done such tables before, and believe me, this is not reusable. So all these mistakes of preparation of data lead to limited reusability. And in engineering, especially if we talk about reusability and openness, we can think about open structure, open formats as the gateway to reusability. So in software development, they defeated actually this problem because they have open source, they have object-oriented programming, and they have GitHub, a platform that provides access to this open source and provides tools to work with this and integrate this code. But in mechanical engineering, things are a little bit harder. And this is something that we are trying to fix with SplineCloud. So my team developed a cloud platform, especially to address these challenges. So basically, when I talk about SplineCloud, it's an open knowledge management platform for engineers and scientists. It is open, and it provides tools for knowledge formalization and reuse in your mathematical models. So we have tools for, so with SplineCloud, you can create repository, process data, and reuse it in your code using our API. So when you work with SplineCloud, so there is a very simple and basic pipeline. You create repository for your data. You upload data from your either simulation, either calculations, and you define data sets and data. So if your data sets are not clean, you can extract this data, subsets of this data with our tools. And essentially, if your data is graphical data, for example, you are conducting research and you have a graph, or maybe it's historical data from some experiments, then you can apply our integrated tool for data extraction from graphs. And after that, chances are high that your data represents some relations between parameters. So we provide a tool for advanced curve fitting, which helps you define some models in your data. And these models and data sets itself, you can reuse in your code using our API. So currently we provide client library for Python and MATLAB, and we are planning to support other languages. So here we accept contribution. So instead of speaking a lot about SplineCloud, I would like to switch to this use case to explain how it works and how the whole process and the idea of reusability can transform your approach to design automation. So in this example, I want to talk about the wing automation process. This can be a wing of aircraft or unmanned aerial vehicle. It doesn't matter much. It's more about how we set up this problem. So I want to start with basic principles. Many of you are probably familiar with these principles, but I need to cover them just to have a nice smooth path from the beginning to the final solution. So as we know, the lift force and drag force are formed due to the airfoil shape. So because of the difference of pressure on upper and bottom surfaces of airfoil, we have this uneven pressure distribution, which provides lift and drag force. And engineers came out with two coefficients for that. There is also a coefficient for pitching moment. I just don't exclude it here from this example for simplicity. So we have lift coefficient and drag coefficient. And this coefficient essentially provides us with information on how lift force and how it forms. And it depends actually on the velocity, on air properties, and more of that, it depends on the shape of the airfoil. So when we design an aircraft, the shape of the airfoil is usually the number one question. What airfoil should we use for our wing? Because wing is the main thing in the aircraft. And there are general recommendations on airfoils. So for centuries, engineers created different types of airfoils. And now you can select from the whole range of these airfoils. So there are general recommendations. So if you, for example, developing a high-speed aircraft, maybe long-range aircraft, you probably want to stick with low camber profiles. And If your target is the aircraft with high lift and low speed, probably you should take a look at deeper camber profiles. But thing is that it's not the only information that we can use. It's not essential enough for us for developing the aircraft, because we want to know exactly which airfoil select. And because in engineering we face multi-physics problems, there is also a question regarding strength, regarding rigidity of the wing, and we have to account for this. And all these profiles, wing profiles, really depend also on the inner structure and materials that we use. And the only way to give the right answer for which airfoil we should use for our aircraft is to go through mathematical modeling process. When we model specific airfoil, we model internal structure, and we solve for some equations, we consider constraints, and we come out with the optimal solution. And to do that, we need to process some data. So as for the airfoils, we have data on airfoil performance. This data was obtained for the many years from wind tunnel tests and from simulation. We have nowadays open software that provides us with the ability to calculate these properties for airfoils. And there are resources that already have this data, for example, like airfoil tools. Probably familiar with this resource if you have ever experience with designing aircraft. So the thing is that processing this data, collecting this data is mundane work. So you have to spend some time. For example, with the same airfoil tools, you have to download those data sets, you have to process those data sets, and you have to build collections, create folder with those things. And this goes through this data management process, which is not very pleasant work to do. At the same time, once we have this data on SplineCloud, you will see how it simplifies the work in design automation. But data on airfoils is not enough for us to go with, because we know about 3D effects, we know about the vorticity of the wing, and we know about the this wind load curve that says us how actual lift coefficient drops because of these vorticity effects. And this effect also produces so-called induced drag. So we have also account for this in real case. And to understand how we can calculate this drop of lift coefficient, we want to understand what is the planform of the wing, because the planform of the wing impacts significantly our aircraft. And similarly to airfoils, engineers came out with numerous shapes of the wing planform. So there are also general recommendations. So if you, for example, designing a low-speed aircraft, you probably will want to use rectangular wing, which is the simplest form probably, but it's not the most efficient one. For example, if you're racing for efficiency, you may want to use elliptical wings because they produce the lowest induced drag, but at the same time, they complicate manufacturability of the wing, and so on. So we have straight planforms, we have swept planforms, we have tapered wings, which is just approximation for elliptical wings. And if we design high-speed aircraft, we may use some swept or even delta wings. And especially if we take care about controllability and maneuverability, we may also incorporate some sweep angle for our wings. But again, we want to know exactly what planform we should use. And we don't have this answer because we don't have answer for the rigidity, flexibility, the mass of the wing, and so on. So still we need to go through this mathematical modeling process. And when we start looking in the literature and trying to find out what is the function of the lift distribution along the wingspan, we can discover some knowledge about this. We can discover that two parameters influence this mostly. It's the wing aspect ratio and the wing taper ratio. So the aspect ratio says us about how long is the wing compared to its root chord, and the taper ratio says us how the tip chord is smaller than the root chord. So we have this kind of shape. But at the same time, when we start to try to find the empirical formula for this, we may fail because there is so many things incorporated in these lift distributions that you may end up with nothing, actually. You may find empirical data on rectangular wings, but for some complex wings, it's really hard to find some empirical data that you can rely on. And this is when we come to the idea that we need to perform some analysis, numerical analysis, and maybe run some CFD analysis. And this comes to the question, what CFD tools should we use for that? Should we rely on heavyweight software that incorporate finite element methods and solve for Navier-Stokes equations? Or maybe it would be enough for us to use some lightweight software and maybe open software. So it really depends on how much you pay attention to the tolerance. So how exact model you are building. So in our case, we already made some assumptions, and you will see new assumptions that we will make. And making these assumptions lead us to the solution that probably we don't need heavyweight CFD solvers. So we can stick with something simpler but reliable. And these are two tools that you can use. It's OpenVSP, open source software developed by NASA, and another open tool is XFLR5. I haven't used the second one, but I used the first one. So even with these lightweight tools, they incorporate methods. For example, OpenVSP incorporates panel method and vortex lattice method. They are really simple and converge incredibly fast comparing to finite element methods. So it just takes seconds for convergence, but still we have to waste some time. So get ready for some handwork, setting up the model, setting up the speed and so on, and especially processing results. Because even using these fast converging methods, I spend more time on processing results. And this is exactly what I'm talking about, reusability, when you don't need to process this data. So here is the win that I analyzed. So I used swept win just for general understanding of the relations. And in this example, I used the fixed taper ratio. You may ask why I decided to go with this constant taper ratio. The thing is that when you look through the literature, you will find out that taper ratio is it should be somewhere in between 0.6 and 0.8 to have a minimum induced drag. So there is not much reliability in this term. So I decided to go with a constant taper ratio just to relax this additional variable in our system. So in this problem that we will take a look today, we will vary the aspect ratio and we will vary the sweep angle of the wing and try to find out what is the lift distribution function actually for the wing. And for this, I proposed we use OpenVSP, and I used this for this example. And here I made some new assumptions, simplifications, just for this demo purpose. You can use your own setup for your task, but for this task, I used no geometric twist, meaning that root chord have the same angle of attack as a tip chord, so there is no twist in the wing, and there is no aerodynamic twist, which means that root chord has the same airfoil shape as the tip chord. It has greater scale, but the same shape. And as I said, we used constant taper ratio. And the one thing that I try to exclude from this simulation is the influence of the airfoil, because we want to go through different airfoils. So in this setup, the result is not essentially the lift coefficient, but the coefficient of lift coefficient reduced by the airfoil lift coefficient. So in this way, we eliminate the influence of the airfoil in this task. So we end up with the result of reduced lift coefficient, any way you pronounce this in English, so the coefficient of coefficient. So we end up with this function, which relates on 4 parameters. It relates on the point, on the coordinate of the wingspan. It depends on the aspect ratio, on the angle of attack, and on the sweep angle. So this is what we can study, and this information would be more than enough for us to come out with our design. So once we have all these simulations performed and we have defined excluded data sets. Yeah, I forgot to mention. OpenVSP provides you with the result files, the Excel files that are really clumsy. So get ready to dig into these Excel files and extract some data sets and prepare clean data sets. And this is exactly the knowledge formalization process. So you set up experiments, extract data, mark data with metadata, give names to data sets, and this is essentially the process of converting, extracting knowledge and making it reusable. So for that, we can create a repository on SplineCloud, specifically for our experiment, upload our data sets, upload our data files, define relations, and build these functional relations between parameters to understand how this drop of lift coefficient changes with wingspan for different conditions, for different sweep angle, for different angle of attack. And this repository provides us with ability to integrate these results into our mathematical model. So once we have these relations, for each relation we have ID on SplineCloud, and we can use this ID to construct a collection of airfoil, not airfoil data, sorry, to construct a collection of these curves, of these efficiency curves of the lift coefficient. And once we construct this this collection, we can build two-dimensional functions, so-called response surface, which will be used by us as a function in our code, in our process of automating design, in the process of design optimization. So we have this two-dimensional surface, which we can instantly evaluate for any points on the wingspan and for different aspect ratios to give us understanding what will be the drop of lift coefficient. And once we have data on airfoils, we can either find this data, there are lots of resources for open data. You can already find some repositories with airfoils on SplineCloud. You can just approach the same, go the same path, use the same approach, and create a collection of airfoil data, which will say us about how the lift coefficient depends on the angle of attack. And we can create a class of airfoil in our Python code to evaluate for the actual lift coefficient, drag coefficient, depending on the angle of attack. And now we can combine our results. So we can combine and multiply these curves, the curve for ideal lift coefficient for the airfoil and the curve for non-ideal drop of this lift coefficient, and actually build another response surface, another two-dimensional function, which will say us what is the actual lift coefficient depending on the wing coordinate and depending on the angle of attack. So for example, if we set constant aspect ratio, we can create a collection of such response surfaces for each aspect ratio. And of course, we can go through numerical integration to calculate the cumulative lift coefficient for such response surfaces and so on. We can also end up with three-dimensional and four-dimensional response surfaces. It's just the matter of taste how you perform this. Maybe with those three-dimensional, four-dimensional surfaces, it just would be harder to visualize them. But yeah, and another component, the drag coefficient. And with drag coefficient, we can go with the same strategy with a little bit difference, that we can go to literature and find out this formula for drag coefficient. And this formula contains the component, the span efficiency component delta. And there is an article here in reference for this slide that you can use, a great article that provided the overview of different empirical approaches to calculate the drag coefficient. And from this article, I essentially excluded this graph, uploaded to this repository on SplineCloud, and used plot digitizing tool to extract data points for each case, and then apply curve fitting to reconstruct this relation. So now we have ability to extract knowledge from these graphs and convert it into reusable form, into the two-dimensional function in our code, which will say how actually this delta coefficient depends on the taper ratio and aspect ratio. And later we'll use it to calculate total drag coefficient, which is combination of airfoil drag and induced drag. So in this way, now we have clearly defined all functions that we can use to give us the answer, what is the lift distribution on the wing, and what is the drag force acting on the wing. And with these functions, we can now vary many different parameters. We can vary airfoils, we can vary angle of attack, we can vary sweep angle, and we can vary aspect ratio. And for each case, we can instantly evaluate the lift force and drag force. And not only that, we can have this relation of the lift distribution on the surface of the wing. And but this is not enough for us to answer our main question, design question, because something is missing. So what is missing is data on the wing structure, on the materials, on the wing console mass, and other things. So here is the basic setup of the mathematical model. So we can consider our wing console as a cantilever beam, which is loaded by two net loads. It's one of the aerodynamic load that's already clearly defined in our code, and another one is the gravity, net gravity load. And for this load, we need some data from the wing model, and for this we need CAD model of the wing. And what is important about this CAD model, it should be adaptable. It should be adaptable instantly for each airfoil, for each geometry. So probably you can use some CAD engine and API for CAD engine. For example, if you're using, I don't know, maybe SolidWorks, maybe you're using FreeCAD or something else, you can use API for that. But setting up this would take a little bit time. And instead of that, I propose to use the library for Python called CadQuery. This is actually the interface for the Open Cascade CAD kernel, which is a popular open source, probably the only one based on B-splines, and it's industry-grade CAD kernel that is used in many software, and especially in FreeCAD. So CadQuery is a simplified interface for this CAD kernel, and it has a Python interface, so you can use it to create programmatically 3D models. So with this setup, you can retrieve console mass, you can make slices of the wing, you can perform numerical integration, you can do many things, you can calculate the wing section moments of inertia. So you can do many things, geometrical things that are not available without that. And for this example, I want to propose we take a look at the wing structure of this kind. So you can imagine any structure of your own. So if you want to repeat this, you may end up with some longeron structure, classical things. But this is something from the previous project that I was studying. So I was looking into the internal box structure. So our wing console has a rigid box inside. It can be a carbon composite box. It can be fiberglass box, or maybe even aluminum box. It doesn't matter. The thing is that here is a rigid thing, and we only will account for this rigid thing as a element of strength in our wing model. And we have other bodies that we just will not account for strength, but will account for mass. It's a shaper, outer shaper. It can be polystyrene form or some other form, and it may be some kind of cover on top just to protect it from damage, maybe fiberglass cover or something else. So once we have CadQuery, once we have SplineCloud, we can write a little bit of code, and we can create this class for airfoil section, which will be adaptable for each airfoil. So essentially, we can define rules how the internal box will fit into any airfoil, and we can run through this, because we can load data from SplineCloud and we create a collection and integrate this collection in this class and iterate through each airfoil. And most importantly, not only aerodynamic data is available on SplineCloud, you can also define the contour of the wing as a spline and load it into your code, so you don't even have to do some fitting in your code to reproduce this shape of the airfoil, because the shape of the airfoil already defined on SplineCloud. And now, once we have this section class, we can go through this setting up the whole knowledge base model of the wing, meaning we have the 3D geometry. We have methods for calculating lift, drag, and lift distribution. We have methods to assign materials. We have methods to calculate mass of this console. We have methods to calculate mass of sections, and we can define methods for numerically integrate those forces and solve for rigidity of the wing, for flexibility of the wing, using simple formulas from the strength of materials. And this model will allow us to iterate through different designs in the range of our defined design parameters and find the optimal solution in much faster than it would be done with manual work. So compare, you do this manually with some classical CAD system, and you go through numerical simulation on each iteration, multi-physics simulation. You have to solve for strength, you have to solve for aerodynamic load. It will just take you weeks or maybe even months of work. So with this knowledge-based model, this is a simplified model. It doesn't account for many effects, but at least with this model, you can iterate through hundreds of design in just 1 or several hours instead of weeks or months of hard work. And this is the beauty of knowledge-based engineering approach. And what essentially it gives us the opportunity to optimize design, to come out with the optimal solution. I will not speak much about the optimization today because it's really interesting topic. Design optimization, multi-physics optimization is a really interesting topic, but it goes beyond this webinar. I just want to give you the taste of how we can approach solving the geometry for our requirements with this knowledge-based model. Essentially, we can define two nested functions. So one function, an internal function, we can define the strategy to fit the wingspan to the required tip deflection. So we can gradually increase the wingspan until the tip deflection is 10%, for example. And the external function will vary the chord of the wing. So this function will repeat this iterative process of internal function until we have the wing of the area that is needed for our lift force, and it will be the same. It will be with the same tip deflection that we defined. And this is how we solve geometry for required parameters. We can, of course, we can define different strategies for our optimization. It's up to you how you solve and approach this problem. And this is the beauty, because once you have defined this model, you have the source code for this model. And if it's open source, somebody else, or maybe you in the future, can adapt this model and include some new knowledge, include some new ideas, and improve this model gradually. So by time, you will end up with more detailed, more accurate knowledge-based model. But what is knowledge-based engineering itself? So I was speaking a lot about this, but essentially this is not a new technique. This is an old thing that was very popular in the 80s and 90s, and the beginning of the 2000s. And basically, this is the philosophy. This is a philosophy of building such systems, such approximations, but very detailed approximations with CAD engines. The idea is that we define knowledge-based model in order to allow us to forgive some things that we don't know about the system, but at least solve for the main properties that we have, and essentially to enable design optimization. So knowledge-based engineering is essentially about building the expert system, write some code to answer the main design questions and integrate through many different designs. So essentially, the knowledge-based system consists of two main components, and this is critical for understanding the knowledge-based engineering model and knowledge base. And they always should be separated. Why? Because once you include knowledge inside your knowledge-based model, it becomes not reusable, because once you incorporate all these data fitting, curve fitting things inside your code, you may end up with the solution that is not scalable. So you don't have ability to transfer these to different models. And once you have a knowledge base which provides these functions for you, external functions that you just can convert and iterate through them, you can apply this knowledge to very different knowledge-based models. So this is the idea about scalability of things. And all this knowledge-based engineering system, it gives you the ability to input requirements, constraints, define objective functions, and end up with the optimal design. You can define, it depends really on this model. you can end up not only with 3D models, you can end up with simulation setups for verification. You may end up with already run simulations, because if you have API for some numerical methods, some numerical software, you can end up with verification of these things. You can end up with actually manufacturing codes. It's up to you how you define this thing, but the general idea is that you encapsulate some knowledge in knowledge-based model, and some knowledge should be external. So once we use Python, and once we used this beautiful language, it's a powerful language, and it's always tempting to write some more code and give more sense to what we have done. So last year I have developed this open source demo project. So basically I used the same ideas but simplified. So today we were talking about load distribution on the wing. So for this example, I used the knowledge-based model on a simplified mathematical model when we consider the even distribution of the aerodynamic forces along the wing, but just for demo purposes, it's more than enough. And with the library for Python called Streamlit, which is another open source library, but this is the library for building web applications in a scripting manner. So you write some script in Python and it converts the script into the web application. So you define those elements, control elements for user interface, and it generates the full-fledged web application, and where you can deploy anywhere. You can deploy it on premises, you can deploy it openly. So this application is currently deployed on SplineCloud. So the beauty of this is that such applications is not hard to develop because with the knowledge of Python, you don't need knowledge of other languages. You don't even need much knowledge about the web development. So this application essentially utilizes the same approach that I was talking today. So you select airfoils, you select the chord and the span, and it solves for the aerodynamic forces, it solves for strength and for tip deflection and so on. So this is open source. You can find this, you can just go to this app, and on the tab about, you will find the link to the source of this application. And the structure of this application, it's based, as I said, on three main components. It's based on the open knowledge base, which is the SplineCloud in this case. It is based on the our defined knowledge-based model, which is using CadQuery, and it is based on the library for the front end. And essentially, with this approach, we can achieve the I-steep of reusability. We can convert knowledge that we mined through design manuals, through all expertise that we conducted all this work. Now we have the application that can answer many design questions for us. So our application can be in use either for experts and for novices, and they don't have to run through this whole process of data mining and preparing and composing this knowledge-based model. So I want to wrap up and say about mathematical modeling in the aerospace engineering especially, and in mechanical engineering as well. So there is a specifics about mathematical modeling in engineering. It's the specifics lies with the challenges that we face, and challenges mostly relate to a to the large amount of data. These are mainly experimental data, statistical data, material properties, and other things. And while we're missing some data, we run experiments, either numerical or either physical experiments, to discover new knowledge. And this knowledge provides us with new data. And all this data usually contains some relations, some functional relations that we can use in our mathematical model to optimize solutions and to automate our designs. And the answer to these challenges is SplineCloud. So it was essentially designed to address all these challenges of data preparation, data exchange in mathematical modeling process. So I encourage you to take a look at SplineCloud, and while you will work with data, take consideration of how you work with data. Will you make it reusable for yourself, at least in the future? And maybe you would like to share your data with other researchers. So thank you for your attention. And here I will stop. And I'm pretty sure you have some questions. You can drop a message in the chat, or maybe you can raise a hand and ask your question. Thank you for your attention.
Vadim, thank you. was very interesting. I guess Boeing will have any other problems this year after seeing your presentation and development of the aircraft.
Thanks.
Okay, but in any way, so please, your questions.
Vadim, thank you for this webinar. Maybe could you please provide a few other examples of how can we use the instrument, for example, in other fields, not in airfoil engineering, but maybe electrical engineering? Is it applicable or not? Maybe other fields?
Sure. Thanks for the question. If I would be electrical engineer, probably I would be able to answer your question. But since I'm aerospace engineer, I'm more about like the aerospace applications. But I'm pretty sure there are cases. For example, when I was studying robotics, it was a course on Coursera, and we had this data about the optical detector. So there was a data about different detectors, what is the range it works. So the amplitude of this detector against the distance. And essentially, while designing systems, you need this data, you need this relation. So this is another case. So for example, you have also other relations on different other components. For example, on SplineCloud, you can find the data on motors. So each provider of components provide you with data sheets with lots of functions in PDF that you have to process and extract this data. And this is a mundane work. So we done some work for that on the different motors, and now you have the collection of these functional relations that you can incorporate in your quadcopter design. So you can iterate with different motors to find out what motor you should use. And we probably want to do this with propellers as well. But as for other fields, I think I just don't have enough domain knowledge to provide it with some meaningful examples from different domains. But in engineering, it happens quite often that in order to make some model, you need to understand how one parameter relates to another parameter. So I think it's applicable to many different fields.
Thanks. So what can be our next step if, for example, I like the concept and I can try out the airfoil generator on your website, and maybe how can I, for example, try to write my own program with your service? Is it possible right now, or I need to contact you in special way?
No, everything is open source. So for example, I've already provided these links on this slide. So there are links on GitHub. So for example, this GitHub Nomad Vagabond is my username, CQUF. It's a library which essentially is built on these concepts. It's the library for generating wins using CadQuery and SplineCloud. So you can fork this repository and write more code. Currently, it's incorporates only code for rectangular wins, but I will soon add these new things about the swept wins that I'm talking about today. And there is another repository for a Streamlit application. And you can visit also, I forgot to add the link to SplineCloud blog. There is also a SplineCloud blog that you can visit for examples. For different examples, we have an application for gear generator. It's not based on some data, it's just based on knowledge of building the gear, but it's also based on CadQuery example. You can find data on thermodynamics, how to solve the problem of thermodynamics of heat transfer between two metal plates with the use of SplineCloud, and data on different materials. There are many other, not many, there are other examples of usage, but basically the idea is that once we are using open source tools, and we expose our code and we expose data on SplineCloud, you can always iterate through new concepts and add them into your code. So answering your question, Artem, I would say that in order to proceed with this example, you have to start with, if you are familiar with Python, it's great. So you have to start probably with familiarizing with CadQuery if you want to use it. If not, maybe you can adopt other solution. But the starting point would be to familiarize with the code of the existing project and finding out what you want to tweak, what you want to change in this code, something like that.
Yes, thanks. It would be nice if you will send as a follow-up the links and like the very tiny instruction, like click here and you will try out this piece of SplineCloud, for example.
Yeah, I can do that, but these are the links on this slide, so you can just make a screenshot for yourself. And yeah, I can send you the link later, maybe for the whole group.
Can I ask something?
Yes,
about
of course.
Yeah, about the program. Do you use Xfoil? Yeah, and another program for numerical to the method. Yeah,
I used Xfoil several times. Yes. You wanted to ask something more?
Yeah, about CFD or Fluence kind of ANSYS. Do you use this program?
So the idea is that we are talking today about open source, openness, and ANSYS is not open source software. So I would not cover that in this topic, but I never used ANSYS. I used other tools. So remember when I was working in design bureau, we used Nastran for strength analysis, and what we use for CFD, I wasn't using that much. So the idea is that if you have access to these tools, for example, for ANSYS, for Fluent or other software, you can essentially apply the same practice. You can conduct experiment with this software and share the results of SplineCloud in the same similar manner. It doesn't matter which tool you are using for simulation. It's about the manner of organizing this simulation and making sense of this simulation, because conducting simulation every time you have new idea about what we can tweak in your design is not efficient. Efficient is to think about what is the family of design parameters and what should be varied and what data we should be using at each iteration, and perform the range of experiments preliminarily and upload this data somewhere and make sense of this data, ideally convert it in functions that you can use in your code, in your design automation workflow. So you can use ANSYS, you can use other software, it doesn't matter. It's about the approach, about the strategy of building mathematical model and extracting knowledge from simulation software.
Yeah, okay, I understood. Thank you.
There is a question in chat. I may read. Vadim, do you provide any data validation for e-foils and twinks? And what are the applicability limits and associated errors of your method?
Very nice question. Regarding validation of quality, no. And I'm not sure that if you go to other resources, there is any guarantee about the quality of data. For example, if you go through the catalog of airfoils, you may end up with the comparison of X-foil simulation to the wind tunnel test. And this catalog provided by some Dutch university, which one of which I discovered, even that catalog doesn't say that you should use this or that. There are always errors in any method. So if you go through numerical simulation, you always end up with error based on the mesh, errors based on some assumptions about the media, about the flow. So there is no guarantee, and nobody can give you this guarantee because there is always a share of error. What you can do is that once you create repository on SplineCloud, you can clearly define methods that you were using to achieve these results. And by understanding these methods, those who are using these results would have at least some understanding if this is applicable for their case. Because for our case, with this model, we used OpenVSP. And if you go through the documentation of OpenVSP, you can just discover what is vortex lattice method and how this approximates, but you will never end up with some number that says, okay, this is 5% tolerance against ideal case. What is ideal case? Or 10% tolerance against the experiment, which experiment? So these are questions. And yeah, and what was the second question? Sorry.
What are the applicability limits and associated errors of your method?
Yeah, so the same here, because in order to so ideally you can take tools that you trust. For example, you can use NCs, and you can use maybe something else for strength, maybe the same NCs, and you can go through this design method, and you can evaluate this displacement and the lift force. And you can run CFD simulation in NCs fluent, and you can run simulation on rigidity analysis in the same NCs, or maybe in a strand, maybe some other software. And you can evaluate this error. But I haven't done this, so I can't tell you what is the error for that. But there is another thing. If you don't have this ability, and you go through some very simplistic models through design approaches, methodologies. If you're going through old books that say, okay, let's use this empirical formula, then I would say that this method should provide you with better results, because it's made on more accurate understanding of the problem, because you're using simulation results, actual simulation results, and you know what methods you incorporate in this. So, no number, but just some reference. There is a question from Alex.
Yes, can you hear me actually?
Yes, yes.
Oh, cool. Thank you very much for the very interesting presentation. So basically, I have worked on the wings elastic design for quite a while. Of course, I get a couple of questions for you. First of all, I'd like to comment a bit on the example you showed. So basically, to my understanding, basically what you do here is normally what we do is very similar to the surrogate model, right? So you just generate a couple of data sets, then you can do the optimizations and choose. For example, you vary some wind parameters, like at the 2D level for the airfoil, you can vary kind of because you use plane. So then you get different lift drag coefficients. And the 3D level, you can vary the chord or length, whatever. Basically, it's circuit modeling. It is fast, but basically here you still don't do real optimization, right? So you don't have the gradient, or you. My basic question is actually, I know it is possible, but how straightforward you can set up with kind of typical MDO, so the multidisciplinary design optimization. Maybe you can also.
Very good question. Yeah, probably understand your question, but I would say that this is the approach based on response surface model. So the idea is about constructing these response surfaces, and once you have this data, the idea is that you can conduct optimization with any library that you have. So you can use how it's called, OpenMDAO, right?
Yeah, OpenMDAO. That's basically what I trying to say is maybe for your tool or your platform, this is one thing would be very valuable if you can. So basically, you have API you can because it's also open source. So there you can actually set up some real MDO stuff. Then you have more potential to play with, for example, the aircraft wind design or other optimization things. So yeah, I guess it's quite. Second thing is I'd like to ask a bit about the platform, because I saw actually, of course, it's a very interesting thing. You have this SplineCloud. I know there are also some other companies that do also similar thing. I'm not sure if you heard about the Dapta.com from the British company. They do pretty much the same.
I heard about Dapta, and I was looking through the webinars of Dapta. Very, very promising thing. A little bit different approach, but yeah.
Yeah. So basically, I also worked with them. I'm not really worked with them. I don't know the CEO there. I even had the Chinese version for that website. So what I see here, basically, you do very similar stuff, but I see some more advanced things compared to Dapta. But there are probably still something. Maybe you can try to look it out. Will be good for your business model.
Sure. Thanks.
The third thing is, because we know basically those things, of course, you do open source, which is good. Everyone can benefit from it, but still you have to set up everything. Then, as you just already, someone I think asked the question, use access or those commercial package. Basically, API, you cannot priority use it now because otherwise you have to buy the license or other stuff. So we will almost go to all the open source stuff. But then they're actually very practical issue. If some company or some organization, it's not from university, right? Or lots of pure academic exercise. They want to use your platform to do some design, for example, the aircraft wing. How do you actually ensure the safety for their data? Because apparently, if they go for your cloud, which is everything online, then there's something to do with the data safety, all those things, security stuff, right? So that was just something what I could think about it. Maybe it's
Alex, thanks for this question. It's basic question actually. Many people ask this. The answer would be very simple. We have open platform, but we have idea to make closed repositories for companies that will use our closed repositories for their sensitive data. So this would come for money, and open data comes for free. So this is the idea. And regarding the thanks for mentioning OpenMDAO. This is something that I'm discovering right now. So how we can integrate these ideas and make it more efficient and up to date with new trends and new standards. For example, there is another package called Aerostruct, which is based on MDAO, and so there are lots of new tools, open source tools for design optimization, and this is one of the approach of using pure Python library. Like for example, if you set up optimization process here, you can use SciPy. So if we go to this slide here, I set up these functions using minimizer of SciPy library. And you can use something from OpenMDAO, you can use something else. And it's about your creativity, your ability to integrate all Python libraries that in your disposal to achieve optimization process. So this is it. But yeah, thanks for mentioning Dapta. I really want to contact them and exchange ideas. This is something that I haven't done yet, but yeah, they're doing really great job. Thanks for mentioning.
Yes, thank you very much. I'm actually very interested everything in this, especially I think you mentioned somewhere about those aircraft wing, like the wave application, right? I saw somewhere it's also open source. That could be also something very interesting to me, because eventually I did my research aspect. I think I put in the comments. Now I actually work at Harold Watts in Edinburgh as assistant professor. But before this, I was working at TU Delft, mainly for the aircraft wing design. So I had quite an experience with aircraft wings. So good to know you. Always nice. Maybe later we can catch up for some ideas.
Yeah, you can use this link and send me an invite on LinkedIn, and we can exchange ideas.
Right. Thanks very much.
Thank you, Alex. Okay, maybe there are some other questions in the chat now.
Not yet, but there is one general question from my side. Vadim, what are the biggest hurdles you faced in development and launching SplineCloud? What
Can
was
you repeat, please?
what was the biggest hurdles? What was the biggest challenge for you during the development and launching SplineCloud?
I would say currently the biggest challenge is to show up these use cases and explain how everyone can benefit of using this approach, and not only this approach. So regarding the technical side, I wouldn't say that it was hard, because it just takes you time and development and your ideas. And it's hard to imagine what I can answer from the technical side, because I was into this spline fitting and optimization based on spline fitting for quite some time. So before that, I was developing a desktop application for myself for doing the same thing. And then I discovered that while I'm doing this only for myself, I should expose it for public. And then I created this open platform, web platform. But currently, I would say that there are lots of things to do yet. We want to implement surface fitting on SplineCloud, because we want to go with these two-dimensional functions, maybe n-dimensional fitting. Is what I'm planning to do. So this probably my complicated answer to your question, to a simple question. Sorry.
Okay, I see. So in any way, it is very interesting to see the evolution of this project and the tasks that are solved in this field. And I hope that we will find an application for the stress analysis.
Yeah, thank you.
Vadim, hello. Just a few questions, because
Sure.
we know each other, and you know some
Yeah,
my work.
nice to see you, Dmitro.
And I would like to ask, as I understood that your work, first of all, for experts in aerodynamics, but also for experts in conceptual design. Yeah. And
Sure.
is it possible to add more options, for example, inside of your knowledge base, as some like limitless for weight, for maybe loads, for some different options according, for example, requirement specification for new UAV or aircraft. Also, some, for example, standards. For example, some JAR or CS basis, certification basis. Is it possible to add some these options inside of this your investigation?
I believe so. Because what I showed today is a very simple application. It is based on this response surface model or meta models, as I say. But if we go to this slide, you have this knowledge base, external knowledge base, and on SplineCloud you can place all these specifications. You can place tables with all these requirements. It's all about how you access this data in your code. So with the SplineCloud API, you can convert these data sets into you can insert ID for these data sets in each knowledge-based engineering model inside. So each model-based engineering model will have reference to these specific specifications, and if they change over time, this ID will not change, and you will adapt to this model instantly. So it's all about how you write code for this knowledge-based engineering model. So, and since this code is open source, maybe you don't want to open this, maybe you want to make it for yourself. It's perfectly okay, but it's about how you define this rule. So you can place these rules and standards on SplineCloud and clearly defined repository and data sets, and not only you can use these standards, other people can use these standards, since if those are standards, they should be open, right? So this is the idea about this architecture, that you have to split data source from the model, from the code.
Yeah, okay, thank you. Because of course, every new idea, it's a compromise idea, and you understand that a lot of experts in own sphere would like some specific requirements for their sphere, and of course it's difficult, but it's really interesting work, and good luck for you. And I think we will communicate about this topic.
I would love. Thanks, Dmitro.
Okay, thank you.
Hello, everyone. Vadim, one additional question from me. I'm Oleg Galaza, yes, PhD student of NTU KPI, yes. And do you hear me good? Yes.
Yeah.
Oh, okay.
Thank
you. In previous slides, you shown us that you consider some deflection of the wing when you modeling it. Yes, some bending. Yes, and as you know, after when aerodynamic loads acting, yes, we got some deformation, and this deformation of wing has some influence of aerodynamic, and we have some elasticity problem, I mean, yes, and building plan, or are you going to include this phenomena, I mean, elasticity phenomena, which use some, which occur some wing deformation, and consider this deformation as some geometrical twist, yes, of wing and redistribution load after wing deformation, and yes, are you going to do it? And if yes, how do you plan to do what model?
Sure. Thanks for your question. I clearly understand your concern about this approximate model, which doesn't account for aeroelasticity problems that will actually change this lift distribution because of the bending of the wing. And this is one of the approximation of this model. So when we talk about, I probably should return this way. When we talk about mathematical modeling process here, we always have to consider the trade-off between what we can do with our time and resources and knowledge that we have to answer main design questions. And of course, with this model that we took a look today, this is an approximate model. It doesn't account for the change of lift distribution because the bending of the wing. But once you have this model set up and you have this model in disposal from the source code. Currently, it's not open right now because it's just something that I did recently. I haven't haven't updated this repository on GitHub with this code, but I will do this soon. So once you have this, you can include your ideas and you can think about how you can account for these elasticity problems. You can try to deformate this wing model, and maybe you can run a range of simulations for the deformed wings and to see how the change of lift distribution comes. So I think there are lots of different questions and answers that can be applied to this mathematical model. But one thing that we always end up with the model that approximates things, and we have to consider trade-offs between our time and the quality of answers. So this would be my answer to your question.
Thank you. And what I mean, if I have this mathematical model for elasticity modeling, and can I integrate my mathematics, my mathematical model, something listed function in your tool or something? I mean, can I combine different tools, your tools and my function for
Yeah,
create?
I believe it's possible. It's about how your function accounts for the wind platform and the wind rigidity thing. So I think it's debatable. I believe it can be integrated. It's about understanding the source and the methods you used to obtain this function. But maybe you can just write me on LinkedIn or maybe email me, and we can discuss this, because I think the whole approach here is about integrating new concepts and making a model that is more accurate through the community communication. So I would be glad to talk to you on this topic.
Thank you, Vadim. I will do. I understand you.
Great, thank you.
Okay, thank you for your.
Thank you for questions. Very nice questions. Thank you.
Yeah, so maybe some short question to you, Vadim, about the future. And so what is your vision for the future of SplineCloud? And how do you see it evolving to meet the changing needs of the engineering and scientific community? So we need more and more. So how your platform could be adopted? For example, if we talk about the Python nowadays, it's in a not brand new, but most favorable language. If it will be a new one, could you adopt an SplineCloud for the new language and other tools?
Thank you for your question, Sviatoslav. I see the future of SplineCloud as a role that GitHub made for open source initiative in software development, because we have GitHub right now. We have, if we use Python, a different language, we can efficiently exchange these knowledge-based models. We have libraries, but the problem is that our models rely heavily on data, on experimental data. And I see the SplineCloud fits into this ecosystem and provides source for this data and provides a platform for sharing this data and enabling each other to contribute to mutual projects, design projects. So if you go and look through GitHub repositories, there are tons of interesting projects, but very few of them are related to engineering because of these complexities, because there is no solidified, well-defined structure of open source engineering. And I think this will change over time, because we have new tools, we have people that already highlighted about new tools. Alex today talked about Depta, talked about OpenDAO and other source resources. So we have this gradual shift towards open source in engineering, and incorporating efficiently these tools means that we have to incorporate efficiently data that these tools rely on. And I think that SplineCloud will take this niche here to provide the access to this data and provide ability to exchange this data. So something like that. And you had this second part of the question, probably I missed that.
Thank you.
So that's probably I missed. There was another part.
So the other was connected just in a language, yeah. So
oh yeah, so language doesn't matter actually, because we already provide API which you can use with any language. The thing is that we currently support Python and MATLAB with the client libraries, which simplifies access, because once you retrieve data for these functional relations on SplineCloud, you have to convert this data into function itself, into the object in your programming language. And this is done with the client libraries for Python and MATLAB right now, but it takes not really much time to write something similar for Julia, for example, for R, or maybe for, I don't know, for other languages, Mathematica, Maple. So it just takes time for that. So it's not a problem at all. So just about the coding thing.
Okay. Thank you for clarification.
Thank you, Svetoslav.
Hello, Vadim. My name is Mykola, and yeah, it's a pleasure to meet you.
Pleasure to meet you,
Very
Mykola.
nice presentation. Unfortunately, I missed a couple of minutes at the beginning, so maybe my question will not be that relevant. So I'm currently working in a huge Ukrainian UAV company, and we are designing and manufacturing UAVs. So we have both theoretical and experimental data which we want to manage, and we're using ANSYS, and also experiments we're doing them in field. Is there any good way in integrate your solution to our current way of modeling, designing, and then testing UAVs? Because I believe that is a good management tool for our approach. So could you please elaborate a little bit on that?
Sure, Mykola, thanks for your question. I'm pretty sure there is a potential for solving this management problem, because essentially it was designed to solve this this problem. So this is just one use case. So for example, if you're really conducting lots of numerical experiments, there is always a need to manage it efficiently. So I think we can think of collaboration, as Alex asked me about this closed data. So if you have data that you don't want to expose, we can create a private repository on SplineCloud for you, and we can elaborate on how you can reuse this data in your mathematical modeling process if you have some. And if not, at least we can think about how you can structure data and simplify access to this data in your company. So this would be a nice point of contact and starting elaborating on this. So I believe we can simplify your workflow with this.
Okay, sounds great. Yeah.
Drop me a message on LinkedIn, please.
Yeah, ready to discuss future possibilities on collaboration here.
Thank you, Mykola. Thank you.
Yeah, it's look like that's all about the questions. And in any way, it will be, I guess, not the last our meeting, the presentation of Vadim. And my advice to you, subscribe to the aerospace faculty Facebook page, and also you have links on the Vadim's. Where is it? Yeah. for different links. So I would like to wish you stay tuned and see how it will be evaluated and what is the benefits could be from this platform for your researchers. For sure, it's my own opinion, but it's a very powerful tool that may be useful in different sphere, in different directions. It's not only UAV, it's not only aerodynamic, and you just restricted by your imagination. And here I think you have a good opportunity to realize your ideas.
100% agree with you, Svetoslav. Thank you for providing a platform to speak today.
Thank you for your Vadim. It was very interesting.
Thank you.
So thank you for all participants, and I hope to see you in near future again. Have a nice evening.